All right, all right. So we're having no screens here. We're on to our last day of Chapter 2, so super slow and steady. We spent 3 weeks covering Chapter 2. And then we're going to get on to the fun stuff. So to kind of paint the picture for you, like, what have we been doing this whole time? We've been talking about position, velocity, and acceleration. We've been talking about them in terms of x, y. Now we're getting into polar coordinates, nt coordinates. And the whole reason we're doing this is that so we can start solving some real problems, right? So we lay the foundation by teaching you how to relate these positions, velocities, and accelerations. But what we want to get to is actually using them with Newton's second law. So today's our last day in Chapter 2, where we'll talk about geometric constraints and relative motion. But really, I mean, big picture, this is what we're doing. Sum of forces equal mass times acceleration, right? So summing forces from a free body diagram, you guys should be relatively familiar with that from statics. What we're working on right now is writing accelerations. And a chapter down the road, we're going to need to use velocities a lot, so we need to learn those as well. So we've been able to write these accelerations a few different ways. So x, y. We talked about what they look like in polar. We talked just last time about what they look like in NT. Today, kind of one extra piece of the puzzle. What if we have something that's constraining this acceleration or this velocity to happen in a certain direction? Or, you know, you could think like a teeter-totter. And maybe if I know one side is 1 unit and the other side is 3 units, as this thing rocks back and forth, we can link up the velocity at point A with point B. We can link up the acceleration at point A with point B because they're constrained to rock on this teeter-totter, right? So what we've been doing is we've been building all these tools in our toolkit to help us with velocity and acceleration. Next time we get together, it's time to put those to use, okay? So today's our last day on this. Where that's also leading me is that after I teach you sum of forces, you know, this is all Chapter 3, we've got exam 1. So 2 weeks from yesterday will be our first exam. So I'll teach you all this stuff about summing forces in x, y, polar, nt, and then we'll test on it. So the one thing I would like from you right now is a quick show of hands. How many people know, I've gotten several emails, but I just push those aside for now. How many people know that the night of October 11th, the Monday, they have an exam conflict? Just to get a rough number. The exam is from 7:15 to 8:45. So I'm seeing like 5-ish hands, okay? That's good to know. That's a number I can work with. If it was going to be like 50 hands, then I was going to be in trouble. So those of you who have been emailing me with scheduling conflicts or with McBurney accommodations, an email will come out in a couple of days where I'll let you know all that stuff. You know, where we're going to be housing the exam, what the McBurney exam is going to look like. If you have a conflict, when can we make it up earlier in the day, or if we push you back a few minutes, however, we're going to do that, okay? So if you're getting excited about that stuff, just hold tight. Okay, so on to the topic for today, section 2.7. So the first thing we'll talk about is locating particles relative to one another. So we have, in this picture, we're drawing translating axes where, hey, we've set our Cartesian coordinates at some point, you know, here on the Earth. It's locked in. But maybe I've got something I'm trying to do. Maybe this is now an airplane. Okay, perfect airplane. Maybe this airplane's flying along at 600 miles an hour. And skydiver jumps out of it. Maybe it's not convenient for me to write the acceleration, the velocity of the skydiver relative to Earth with our XY system. Maybe in this case it would be more convenient for me to write, hey, how is this skydiver moving with respect to the plane? So maybe, I don't know, maybe I've got a plane, oh geez, this is silly, but maybe I've got a plane with like a, I don't know, some protrusion or something that sticks out the back of it. I don't know why it would, but maybe it has some funny landing gear stuck down. I want to know if this guy falls out, is he going to hit that? So I want to understand his velocity and his position relative to the airplane. So we can do that by relating how the guy's moving with vector addition relative to the plane, as opposed to looking at his position relative to the ground and the plane's position relative to the ground and trying to figure out if they're going to strike each other. So sometimes it's just a little easier to look at things this way. All right, so we can write our position vectors relative to this little xy system. And we're going to assume this little xy here doesn't rotate in time. So it just translates along, always holding its same position. Because remember, if it starts rotating, then when we take the derivative of those unit vectors, we got to account for the rotation. So we don't want that right now. We're just going to move from position to velocity to acceleration easily, because these guys are going to move, but they're not going to rotate. So if we want to do some vector addition, we want to write the relationship between our points A and points B with this little vector that we have between them. So maybe I got this big XY system. I got point A over here. So this would be my vector RA. Maybe point B is off in the distance, a vector from my origin. My vector B. And then what I want to be able to write today is this vector between these two. And we're going to give this guy a name. This is my position vector R. It's going to be of point B, so sub B, with respect to A, slash A. So R of B with respect to A. So this locates point B with respect to point A. But you see what we have here? If I want to write this, I can do that with vector addition. So, hey, my vector B here, R sub B, is the combination of these two. I'm going from my origin to A, and then I'm adding on from A to B. So my position vector RB is really, I can relate it to A. So if I know how fast my airplane's moving, or sorry, not my speed, but my position at this point, plus B with respect to A. So hey, where's my point B? My point B is, I know some position A, and I know how B is located relative to point A. So this is going to be our relative position equation. One thing is that you can swap this around and write it the other way as well. You could say that, hey, what's my position of A? Well, that's going to be B minus this guy. So I could just take it over to the other side and subtract it off, or I could write it as a positive R of A with respect to B. So I've just swapped my subscripts now, knowing that one vector from A looking to B is the opposite of the other vector of A with respect to B. So B with respect to A is the opposite direction of A with respect to B. So if I try to draw that in there, that would just go the other way. So all of this, again, xy system, and we're assuming no rotation of these coordinates. So since we're assuming no rotation of the unit vectors I and j, we're purely just translating. When we take the derivative, we don't have to worry about the rotational part. So if we want the derivative of this to find velocity, it's just my velocity of b is equal to my velocity of a plus the velocity between them of b relative to a. Same thing for acceleration. Just one more derivative. That doesn't seem super hard. Let's put this to use. Try to make a little sense of why we even care about this. All right. So here we go. We've got these two blocks with a funny angle. And we've got block B sliding over the ground. That's our horizontal piece here. Just sliding to the right. While we have block A with an absolute velocity of -4 in the I and -4 in the j feet per second. We want to determine the velocity of B at this instant. Well, what are we looking at here? Here we've got constrained motion of this block A. This block A is sliding down the back of block B. And you think, well, that should probably happen at like this angle, right? That's exactly perfectly aligned with this. So that's what's happening as block A is sliding. But the fact that it's sitting on top of block B, being pulled over to the right, block A looks to have a different velocity. The velocity that it looks like it has, or that it does have, absolute, it actually points at a steeper angle than that. So if I try to draw out what's happening here, the velocity of A relative to B looks something like that. And the way I think of it is, I went in here and tried to look at what's moving. Hey, B is moving right now, A is moving. Let's make our life simple for a second. Take your finger and you stick it on B. Don't let B move. What velocity of A relative to B, that's what you're looking at then. Is, hey, if I'm pretending for this moment in time that B can't slide anywhere, what does it look like A is doing? A should look like it's sliding down the back of B if B is perfectly still, because that's what I'm referencing my velocity with respect to. So that's what I'm trying to describe with this guy. My velocity of A with respect to B. So lock B in place. How does A appear to be moving? That's what this vector is telling us, okay? So we've got these blocks. A and its buddy B. Oh, yeah. So what do we know? We know the velocity of B is what they're asked us for in the question. But we know that it's purely horizontal because it's sliding along this surface. So if I want to write this out, maybe I just, instead of writing question mark there, I could leave it as a constant. But that's just to show us that that's what we're looking for. So it's something in the x direction and 0 in the y direction. That's valuable. I know that it's sliding horizontally. My velocity of A, -4 in the I, minus 4 in the j. And this is feet per second. So A, this angle of this plane, is 30 degrees. But if these guys are equal, A is sliding down at 45 degrees, right? So if we wanted to sneak that in, it'd be 45 degrees. How do we deal with this fact that there's a mismatch between them? Well, what do we know about our velocities, relative velocity? So we'd had that v of b is equal to v of a plus the velocity of b relative to a. That's the equation we just had. So I kind of try to unpack this a little bit and think about what I know. Velocity of b, that's what I'm trying to find out. Velocity of a, got it. Velocity of b relative to a. Okay, so if I held a constant, how would it look like b is moving? This part hurts my brain a little bit, because if I held a constant, we fix this guy, b would be sliding along the plane that they're connected to. But b would intersect the ground, so it's kind of non-physical in the way it looks. Even though we're only talking about b relative to a, so we're not breaking any rules here, as I'm trying to visualize this, it hurts a little because b looks as if it would be sliding into the ground if we locked a. So since that way hurts my brain, we flip it around. I say, hey, I have my velocity of a is equal to my velocity of b plus my velocity of a with respect to b. This one we've already talked about. So this is now, we kind of flip the script here, right? We hold b constant, and a appears to be sliding up and down along this line. So that works better for me. So that's the one I've already drawn here, and that's the one we'll use. Think about it from a vector addition standpoint. If this is the equation we're going to use, my velocity at a is equal to b, my velocity at b plus the velocity between these two. And I cleverly drew these to work out that way. So my velocity of a, that's that purple one, the line, is equal to my velocity of b, so I take this one and I draw it over here, plus my velocity of a with respect to b. That's the little diagram we make. Hey, v of a with respect to b is coming down along that slope. V of b, purely horizontal, they're going to equal my velocity of a. So we're on to something. We just have to write out what's going on here. So my velocity of a with respect to b, that's this guy, it's going to have some magnitude. And then it's got x and y components, right? And we know that angle is 30 degrees. This angle is 30. So in the x direction, it's pointing negative. So minus whatever that magnitude is. And that's the cosine leg. So minus cos theta, in this case 30 degrees, in the I direction. And then it's j component. No, that's this piece. So minus the same magnitude, v of a with respect to b, and that's the sine leg. Super close to solving this. Let's put it together. Let's pop this into our equation. So for velocity of a, I'm going to substitute this out. Minus 4 in the I, minus 4 in the j. VB, that's what we're trying to figure out. So I've got v of b, and we know that's purely horizontal. So I'm just having an I term. Plus the the velocities between the two of A with respect to B. So this is minus V of A with respect to B cos 30, or theta, minus, I missed my A in there. Minus sine theta in the j direction. We're close. I look at this equation. I don't know V of B, and I don't know V of A relative to B. Two unknowns. Oh, so close. But it is a vector. It's got x and it's got y components. So, hey, this is actually two equations. Two equations, two unknowns. I just have to split that apart. So in the x direction, we got minus 4. And on the other side, VB minus V of A with respect to B cos theta. And now I'll sneak in my 30 degrees, just so we know what's known. My y term, another minus 4. And this one is only minus V of A with respect to B sine 30. So I've just broken our vector equation up into its xy components, which we can then solve. So sine of 30 is a half. V of A with respect to B is 8 feet per second. Take that, plug it back in, and you'll find VB. 2.93. And that's in the I direction. So understanding how the one piece moved relative to the other piece, being able to set that up in our brain and looking at this and saying, hey, I've got that angled piece. These guys got to be sliding on one another. That's going to be their relative motion. That's the part that we need to get today. And if you can get that, the whole problem isn't very hard, but it's seeing that, hey, this guy slides and its velocity relative to B is going to have to be in that angle. So if we can make that jump, we can solve these problems. That's only one type of constraint, though, that we're going to look at. We're going to look at a couple other things, too. All right. The one other constraint we'll spend quite a bit of time on is whenever we have ropes linking things together. So one thing that we'll do in this class, most of our ropes that we'll talk about, we'll say are inextensible. So their length doesn't change. If we have A to B connected by a rope, whatever this length is, that's going to stay the same. You can imagine as B here slides down the hill, A has to slide up, and vice versa. As A slides down the hill, B has to go up. If the rope is can change lengths, well, who knows what's happening then? I could invent something where they're both sliding down and then sliding up together because they're on little rubber bands. That's for another day or another class. So for now, we want to just be able to write how these move relative to each other in kind of a systematic way. This one, you can just eyeball and say, well, Sonny, if B goes down the hill a foot, A's got to go up the hill a foot. Well, yeah, cool. It's only like one rope. What if we put multiple ropes together? What if we have multiple pulley systems? You know, as engineers, we think pulleys can help us out. Like, instead of pulling up 1,000 pounds, I could have 1,000 pulleys and pull up 1 pound, right? So how do we write this out in a systematic way? we'll do it for one pulley, and then I think it can make some sense then. So when we have ropes and pulleys and all, there's going to be a lot thrown at you visually. Not in this case, but in general. So what we want to do is we want to start unpacking that in an easy way. So the way I think of it is that I'm going to write one equation for each rope. If I got two ropes in here, I'm writing two equations. This one's easy. I got one rope, I'm writing one equation. That one equation is going to describe the length of that rope. So what's happening to the length of AB? So we want to write an equation for the length of AB. I want to go and I want to add up all the different pieces that contribute to the overall length of AB. So I want to figure out, hey, how far is A sliding up the hill? How far is B going down the hill? And maybe what's this little constant piece over them? If I traced out the exact path of this. All right. So the gotcha, as we write this, we want to set up a datum for measuring these pieces. So when we're measuring the position of something to something else, convenient to fix our 0 point at a fixed point. So this pulley's not going anywhere, right? It's stuck at the top of the hill. But A can slide up and down. So I want to set my datum in a fixed location. So set datum to fixed point. And measure relative to that. So for us, I'm going to measure coming down the hill from my fixed point to A. Call that S sub A. Want to do the same thing. I want to measure from a fixed point on that rope's path down to B. SB. All right. Write our rope equation. So this rope is made up of all these different parts. It's SA plus some little constant piece plus SB. If we're assuming this rope is inextensible, it doesn't get longer. Well, now we're in the case where if I took the time derivative, my length doesn't change. That goes to 0. So 0 on this side. Time rate of change of my position A, that's the velocity of A. Plus the derivative of a constant, 0. Plus the derivative of my position B is my velocity B. So what I get here, that my velocity of A is equal to the opposite of my velocity of B. For a single pulley or a single rope with just two things connected, as one goes up, the other goes down. Hey, your brain probably could have saw that. Once we start building complexity, though, it's nice to have a process for doing this. Write an equation for each rope. Work your way around it. Take a derivative. Hey, if you want to take an acceleration as well, you can get your accelerations linked up. If this was flat plane and you were looking in tangential accelerations. So, not terribly tricky. Now, the gotcha here, positive and negative. Well, what the heck does this mean? It's all going to be referenced with respect to how you've drawn your datum. Not with respect to x, not with respect to y, not with respect to some weird angles. Just how you've drawn your lines. So, velocity of A. If my velocity of A is positive, I'm moving in the direction positive, increasing from my datum. So velocity of A positive, this would be like a positive velocity A. What's B doing? B then, negative. This is negative velocity of B. It's moving towards the datum. That distance is getting shorter, right? So if in your brain you think, well, this is going down and to the left. Those are two things in a Cartesian system that say negative, negative. Well, I don't care. I'm calling it positive because it's getting longer with respect to the datum we've drawn. And B, hey, this is moving up the hill. Up is positive. No, it's not. It's getting closer to the datum. So again, in this case, we got to look at our position relative to the datums for the sign. All right, we've already talked about this. This is just saying your datum must be defined as a fixed point. So you don't want to try to define your datum relative to something that's moving. All right. One is a little bit spicier. So here I've got a pulley that comes down. All right. Let's try to follow our rules here. All right. How many ropes do I got? I count through and I've got one rope. You think, hey, no, son, you're lying to me. You got another rope up here. That one doesn't count. It's just sitting there. It's not moving. Not changing length, not moving. It's just fixed. So that one to me could be any anchor point. I've got one rope that I'm trying to track. All right. I want to write out the length of all these different pieces. But first, maybe let's set our datum. We're going to go from a fixed point to the points we're interested in. So I think A is pretty easy. I got this pulley in the corner, and A is moving to the right. So this is going to be my datum over here. And this is going to be my distance, S sub A. How far are we moving with respect to our first datum? The second one, our distance for B. All right, well, maybe that's not intuitive. Right? How come we didn't draw it all the way to B? Well, B is just hanging on this cord. Wherever this point and this pulley goes, box B moves with it. One goes up, one goes down. Velocity, linked. Accelerations, linked. They are rigidly connected. So measuring all the way down to the box versus measuring to the pulley, kind of doing the same thing, right? Because they're essentially linked in space. And then, instead of measuring from the top, a fixed location all the way down, I can measure from this pulley, because this is also fixed in space. And if this thing went so high that it was above this pulley, probably bad things would happen. Our system would start to break. So this is like the easiest fixed line to work off of. This is fixed because this pulley is not changing anywhere. And then this first part of the rope is just some constant piece. It's always just going to be the same length. So if we start working our way through this rope, what do I got? I got this first constant piece. And then I've got this section, SB. And then I'm looping over here, another constant piece. And then I'm going back up, SB. And then I have a constant piece. And then, from the top pulley down to the bottom, hey, this is always fixed as well. Another constant piece. This is my C4. Lastly, I've got my distance to point A. So this looks really gnarly, but it's really just some constant plus 2, that's SB. I'll write it out, plus SA. Just like we did before, take the derivative, rope isn't changing length, set that equal to 0, because it's not changing. My constant falls out. My 2 times the position of B goes to 2 times the velocity of B, and position of A goes to the velocity of A. So this leaves me with 2VB equal to minus VA. For every 1 unit that B moves, A moves 2 units. That's what pulleys do, right? So that's what we have here. Again, let's think about the signage, just so we're not messing this up. So as the velocity of B, say I move this 1 unit, so B is going to come down 1 unit. That's positive because I've moved in the direction of SB. I moved in the direction that I'm referencing its datum. So let's call it 1 meter. So as B moves down, it's pulling cable, so A has to slide the other direction. How far does it go? If VB is 1, VA is 2 meters. And its direction, negative. Well, hey, I referenced SA positive to the right, so negative will be to the left. And like, yeah, that's what it's doing. And hopefully, we can look at this and let's play these games where we just pinch them and we pull, like, oh, oh, oh. And we can do that back and forth and we can tell our brains that, okay, what I need this thing to do mechanically is what I'm expecting it to look like if that cable doesn't change length. One more. So here we've got a system, 1 rope, but I've got A and B on these sliders. And you think, like, okay, as A moves, B is going to move. Because I got this triangle messing us up, and I got the Pythagorean theorem of A squared plus B squared equals C squared, when I move A, B moves a different amount, right? If I'm thinking purely along the direction of this slider. So we've got some work to do. But that's overall what we're trying to figure out. So A and B are connected to a cord that passes over a pulley at the top, at C. When A is located at D, B is 24 feet to the left. So they're just giving us some information about the geometry. So I've got a slider. When A is located at point D, we're going straight up here. Point B is located 24 feet. And we know this is 10 feet tall, so this is perfectly drawn. But what we want to know is that if A is moving constantly at 2 feet per second, we want to find the velocity of B. We want to find VB. When A is 4 feet past D. So 4 feet over. So what does this look like? A is slid over. It's created some new triangle. That's going to pull B over a little bit. We want to find our velocity of B at this point. We're going to assume that this cable doesn't stretch. So Okay. Let's jump back to high school, middle school, just to figure out our geometry. What the heck's happening with this thing? We got a bunch of triangles to deal with. We can look at our geometry to figure out the overall length of the cable. Because we know at some point, this triangle BDC, 24, 10, and I just solved that, 26. All right, so I've got that. This 26 is equal to the square root of the other two pieces squared. So the total length of my rope, L, is this 26 plus this 10, right? Because this is all the rope. Just a little bit of geometry unpacking. How was this thing built up? Okay, the part that we just worked on. The equation for our rope. The length of this rope is our distance to B and our distance to A. So if I wrote that out, here's B, here's A. They slide horizontally. So this datum point, it's going to be fixed in location, but I'm going to allow it to track the distance of the rope. So it's going to kind of rotate a little bit. So my rope, if this is point C, it's going to be this segment BC and this segment AC. If this rope is constant and we took the derivative of our length is 0. BC dot plus AC dot. Hey, they're going to be opposite. That's our constraint. That as one section of the rope gets longer, the other gets shorter in equal proportions, 1 to 1. That's great, but we can also write equations for what these guys look like because they're just triangles. Okay. All right. So I have this triangle built up, and I'm given information for how fast A is moving and its position relative to D. It's moved 4 feet. So that's going to be the point I set my datum at. And I can look over here. Call that XA. I'm trying to figure out how fast B is moving when XA is 4. Well, I got that datum set. It's also convenient to write what's happening at B. But now what I have is I can relate xb and xa, two of the lengths of their cable. So if we do that, BC squared equal to XB squared plus 10 squared, just a right triangle. Same thing for AC. AC is that 10 squared plus XA squared. How is XA moving? The relationship I have relates to their velocities. Hey, let's take their time derivatives to get from lengths or positions to velocities. So my time derivative of this first one, bring the 2 down, 2bc times its time derivative, bc dot, equal to 2xb times its time derivative, xb dot. The 2 and the 2 will cancel. I have my compatibility written in terms of bc dot, so that's the term I'm going to try to get rid of. So I do that by dividing by BC. I'm going to get that exact same thing if I do the derivative of my other side, my A side. So I'm going to fast forward that piece just a little bit. I got AC dot is equal to XA dot over the length of AC. Again, just taking the time derivative. I just skipped this step for this one. Okay. These guys are opposites from our geometric constraint. So we can make these equal to each other. XB dot over BC is equal to the opposite of AC. So minus XA dot over AC. I'm trying to figure out the velocity of B. That's XB dot. So I'm bringing the other stuff to the other side. XB dot is equal to minus XA dot over XB, the length of BC over the length of AC. Whole lot of work. We know a lot of this stuff, though. So we know XA is 4 feet, given to us in the problem statement. XA dot, 2 feet, moving to the right at 2 feet. These other guys, we don't know, but we can get them all from geometry. So AC, this distance here that we need, that's just going to be our 4 feet and our 10 feet. This is AC. BC, the other distance we need, I got this whole rope, which is a total of 36 feet. We started in the beginning. Hey, this side is 10.77. This side is BC. 25.23. And then XB, just some more geometry. We just solved for BC. We know this is 10. That's XB. Okay? I'm out of time, so XB dot is equal to minus 0.81 feet per second. Very quickly. Minus 0.81 feet per second. Negative, but the direction I drew xb was positive to the left. So this guy is actually moving right. All right, all done. Next time we meet, we'll actually start summing some forces, do some Newton's second law.